All right, so we have a problem in which we have a toy gun with a spring mounted inside it, and you are going to place a dart on that gun and push it back. So obviously this is my gun. So it is all pushed all the way back with the dart on it, and that dart has been displaced by a displacement. So initially it's at 0 at the point where it is going to be released from the gun, and it is pushed all the way back to the point where the distance is 6 centimeter. So x initial is 0, x final is 6 centimeter. Basically, you have compressed the spring inside the gun by 6 centimeter distance. You have done some work on the spring, and that work and the dart, and that work has been stored as its potential energy. Okay, you're gonna let it go. It will be released. When you fire the gun, it would be released with the speed Vf. That is the final speed. Good. What's the initial speed of the dart? So we are starting from the point when it is here and the point when it is released and leaving the gun. Okay, with some speed Vf. Initially, it is at point A, mounted at rest with some potential trapped in the spring. Then you fire the gun, and it is released. It is released with some and leaves the gun with some speed Vf. We want to know what is this Vf. K for the spring is given as 250 Newton per meter. Good so far? So there is a gun, dart mounted on it. It's very similar to the projectile motion lab where you mounted the ball on the spring. You push it back. So you do some work on the spring, and that work is stored as the potential energy of the spring and the ball you had mounted on that projectile. In this case, it's a dart. What's the initial speed? Is there any information? We know that initial position is 0, final position is actually initial position is this, final position is this when it is released. Initially it is at 6 centimeter, it is released, it reaches to x equal to 0, and there you want to know what is the final velocity. Is there any information which is hidden? Do we know the initial speed of the dart? It should be 0 because it's mounted. It should be 0 initially inside. It's not moving. Even though it's not given, but when it is released, just before being released, it is at 0 speed. What energies we should consider? There are 3 energies in hand. One is kinetic energy, one is potential energy elastic, one is potential energy gravitational. Which one we should consider for this particular problem? Good, because the spring is involved. Okay. Okay, yes. and it moves. When it is fired, the dart will move. There must be kinetic energy involved. How about gravitational potential energy? Will that affect anything? Dart is not moving vertically. It's only moving horizontally. Will gravity make any difference? No. So we will not consider the gravitational potential energy for this problem. So initially, energy at point A should be equal to energy at point B. Is that right? How do we know that? It always remains the same. Total energy of the system always remains the same. That means potential energy elastic plus kinetic energy should be at point A should be equal to potential energy at and kinetic energy at point B. Make sense? Robert, you know what we did here? Why did we put the energies equal to each other? Evans. Does the total energy of the system always remain constant? Yes. So does it matter which point the object is in during the motion? E would always be the same. If it has initially 63 joules, it will have the 63 joules all through the motion, no matter where it is, here, any point under consideration. Total energy of the system always remains constant. And what is the total energy? In this case, it's going to be the sum of elastic and kinetic. Okay, because these are the only two energies which should be the part of the system. The gravitational potential energy is not changing because mgh requires the object moving under the gravity. And in this case, it's not moving under the gravity. Okay, it's mainly the potential energy push. Okay, the spring potential energy push. There is no gravitational energy. So half kxi square plus kinetic energy A. Let me write down the formula now. mvi square equal to pe half kxf square plus half mvf square equal at b. Good? Do we know everything here? Zero. What is missing is the mass of the dart. That we don't know. So that is also the piece of data . 10 gram. Okay, use that value and find the final speed and give me the number. Solve the equation for final speed. 3? 0.3?
0.3.
Okay. Sorry. Not enough space. Point 3. 30? It cannot be that big. Because it has been displaced by very small. 250. Yeah. Mm-hmm.
Okay, I went 1 meters per second, not centimeters per second. That might make
Oh.
sense.
What's the answer? This, if I plug in all the numbers, this is going to look something like this. Half 250 times 0.06, it's the distance in meters by which the spring has been compressed, plus 0, because initial speed is 0, equal to this one is final position is 0 as well, plus half m vf, m is 10 gram, and you do need to convert it to kilogram. You converted it? You did it? Divided by 2. Rest you can solve probably. You have to solve for VF. So half would go away on both sides because it's the same constant on both sides. So basically it should be, VF should be equal to 250 times 0.06 times, square divided by 0.01. This is square. And then you can take the square root. Whatever is your answer here. It's 99.4. All right. Any questions for this problem? SI units. You always convert everything back to SI units before you can solve them together, because see, this constant is designed with Newton and meter, correct? If you use any value in your problem which has centimeter with it, it's not consistent with this, okay? Because if you want to solve everything in centimeter, then this should be in centimeter as well. So either everything should be converted to this, but the preferable way is to convert everything to SI units, MKS system, okay, where mass is in kilogram, okay, length is in meter, time is in seconds. Because these all of them, Newton also involves, if you remember, Newton is kilogram into meter per second square, right? So everything has to be consistent with the constant that you are using in the equation. You cannot multiply or divide or put them together in one equation to solve in order to get the right value. Okay, it will be off. Okay? And I don't know why it's a lab, always a question. Why do we have to convert? This is, mass always has to be in kilograms, no matter what. In physics, this is in the first chapter that you learn that the set of units, you always keep everything in it. Little bit more complicated problem, okay, where we're going to deal with all three energies. So there is a building, okay, and then there is some sort of trampoline down there with a spring mounted under it. Okay. And Fiorella is ready to jump. So she is standing up there on the top of that building. I hope it's not that high. It's only 2 meters high from here. From the platform. Okay, so initially her speed will be what? 0, right? The mass of this person, so VI initially 0, mass is 50 kg. The height above the platform, if we take the platform as the 0 point, like a reference line, so this distance would be positive 2 meters initially. But it's totally fine to take the initial position as 0 and take the distance as negative too. That should be fine. But I am taking the central position as its reference line. K for the spring is 8 times 10 to the 3 Newton per meter. Very heavy, very strong spring to support that platform. So she jumps on it, and what should happen? She's going to bounce back, but before that, she's going to push it down, right? A newer position, which should be somewhere here, correct? So platform has moved slightly down because she has pushed on it, and the spring is compressed, and this thing has come down. So this is the initial position, this is the final position. We can call it as distance d. It is compressed by distance d, okay, or negative d, okay. Because it's below our reference line, it's going to be a negative distance. We want to find this d, that if she has jumped from a height of 2 meters on a platform with a spring constant of 8 times 10 to the 3, how far this platform is going to be pushed down under her weight. Okay, and you want to know what is the distance, the final distance achieved. Obviously, the next step would be it will come back up, and it's like the trampoline effect. She's going to go up again, but we don't want to go that far. It's the first part that when she jumps, touches the platform, pushes it down. Good? So far? Will platform come to rest at some point? When being pushed down, yes, it will stop, and then it will move again. So its final velocity will be 0 here. Okay? Let's start working on it. What do you think? What should be the strategy to solve the problem? First of all, what energies are involved? Elastic. And is she right? Gravitational must be taken? Yes. So initially, how should I proceed? This is position A. This is position O. This is position B. How should I proceed? There could be multiple steps involved, or there could be single step involved. Okay, we will see what would be the best way to do it. Now I'm going to take you the long way, and there is a reason for it. I want you to learn that what happens on the way. Okay, initially when she jumps, she has all the potential energy here. Is that right? What kind? Only gravitational, right? There is no potential energy at point A potential energy due to spring at point A because it has not in use yet. She jumps down, she converts all her potential energy to kinetic energy, right? So far, no elastic potential energy. When she touches the platform and this spring is compressed, where would all the kinetic energy go? Into the spring, and it will go down into the spring potential energy. Correct? So how is this working? Potential energy, gravitational, going into kinetic energy going into spring potential energy. All right? Next step would be spring potential energy would go into kinetic energy, and then again back to the potential energy due to gravity. So these steps are involved. If you understand that, believe me, half of the problem is solved. But if you don't understand this part, that how the energies are changing into each other, then you will not get the meaning behind what I write in mathematics. Okay? But mathematically, the energy at point A should be equal to energy at point O should be equal to energy point B because it's a total energy. Correct? You all agree? I'm going to take this part of it. I'm going to compare these two energy, EA at EO. EA is mg, what is it called here? Y plus half kxi square plus half mvi square, energy at 0, mgy Good. Now, this is M. M is 50 kilograms. 9.8 Y is equal to Y. This is 0. This is 0. Equal to mg. This is 0, 0, half m, which is 50 Vf square. See what happened here? Initial position is at y, which is also known, that is 2 meter. So in next step, you can plug that into also this 50. Apparently, this is cancelled. So Vf will be equal to 9.8 times 2 equal to look at it yourself and tell me if that makes sense to you. Yes. Which ones are 0? Because initially speed is 0, so kinetic energy initially would be 0, right? Yeah. Spring is not compressed yet. So there is base, it's not involved yet. So it's not in action yet. Because when she jumps off, spring stays the same until she touches it. For the whole system. I put all three energies together. Okay? You could have avoided it. I mean, if you don't write it, it's not a mistake. I didn't want to put it there. Okay? Because initially this is not involved. We will add the numbers. We will use the same equation second time for here, and there will be potential energy. Okay? Make sense? Okay. And this one is 0 because it has touched the platform. Potential energy is 0. Okay. This one, again, this is due to elastic potential energy. Elastic potential energy is 0 yet. Okay. At that moment, it's 0. What's the final speed? 6.3. Good. Is there any other way that we know of for finding speed other than the energies? Kinematics. It's like a drop object. You want to know the speed at the end of 2 meters. Yes, you can do it. You can use the kinematics equation. But once energies are involved, it becomes very, very easy. Okay? So that is a new way of solving problem. There are several problems which you can solve using both methods, using kinematics equation, using energy equations. But usually it's very convenient to work with the energies. Okay? And in some cases, it's just the only way to solve the problem. Now, we know the speed at point O. So energy at point O should be equal to energy at point B. Again, I'm going to write all of them. Now let's go through each one of them slowly. Do we know mass? Yes. G? Yes. What about Y? No. What is Y at point O? 0. Right? Because it is on the platform. Okay? So this Y is 0. Good? Half K, we know K. Xi, do we know Xi? Initial position? Actually, let me fix one thing. Let me call this Yi instead. And this one, because it's a vertical position, so X is not making sense anyway. K, Yi, that is also 0. Good. This is the same. Yi is 0 here, Yi 0 here as well. M, we know that. Do we know Vi? Is it 0? At point O, it should be 6.3. You are not starting from the beginning. You are starting from this center point. Here, M known, G known, Y is what? Huh? Yeah. Yes, minus D. Right? What about K, we know. What about YF? That is also minus D. We know M. What about VF? 0. It has come to rest. It stops. Zero plus 0 plus half 56.3 square equal to minus 50 times 9.8 times D plus half 8 times 10 to the 3 D square. Looks good? I did nothing, but I just plugged in all the numbers there. Initial speed is 6.3. So on the left hand side, all you have is the kinetic energy. So at the central position, all it had was the kinetic energy. Then final position is Y is negative D, or YF is negative D, YF is negative D here. Here it becomes positive because it's ky square. Square makes the negative D positive. It cannot make this positive. This is negative. You have a negative GD, mgd, and plus half k d square. Fine? What equation it looks like to you? It's a quadratic equation. You're going to solve it. Okay? It's going to be 4 times 10 to the 3 d square negative 50 times 9.8. 490 d. I'm going to take this whole thing to the right hand side and solve it too. Times 992 0. Do you think you can solve it? Get two values? Go ahead, solve it. First thing, you should divide the whole equation by 4 times 10 to the 3 or 4,000. It gives you, let's see, what I have here is d square minus 0.123d minus 0.248 equal to 0. Now it's further simplified. You can solve it, okay, and come back with the answer. You're going to get 2 answers, okay. So do not wind it up. We will discuss that in next lecture. One of them should be acceptable and the other one should not be acceptable. I don't have the final roots here, so I cannot tell you what number you should get. So you are the one who is going to solve and bring me the numbers.